On July 1st, 2025, a telescope in Chile picked up an object that didn't look like anything routine. By July 2nd, the discovery was confirmed, and by July 3rd, astronomers agreed on the key point. This visitor was interstellar. It was named 3I Atlas, only the third object from beyond our solar system ever verified. From that moment, the public story took shape fast. Within days, the headlines were already settled. An interstellar comet, a rare but natural traveller, nothing to worry about. The problem is that the data never lined up cleanly with that calm framing. If you step past the press releases and look at spectra, brightness curves, and observing logs, you immediately run into contradictions. They're not vague mysteries. They're specific measurements that don't fit the usual comet playbook. Over time, those mismatches stacked up into a full pattern. Some are small, some are huge. Together they point to one uncomfortable reality. Much of what people were told about 3I Atlas was either wrong, overconfident, or presented in a way designed to make the weird parts feel harmless. This is not a conspiracy claim. It's a forensic read of published numbers. Start with the most basic label. We were told 3I Atlas is just a comet, but every comet ever studied in our solar system shares a common chemical signature. Water ice dominates. Carbon dioxide is present, but usually as a secondary contributor to activity. When solar heating kicks in, water drives the outgassing and shapes the coma and tail. Atlas flipped that ratio. Observations from the James Webb Space Telescope showed a coma made of roughly 95% carbon dioxide and about 5% water. That isn't merely unusual. In the catalogue of cometary science, it's essentially unprecedented. You might hear a simple explanation. Maybe Atlas formed in a much colder region than our comets, so its chemistry is different. But that explanation struggles under scrutiny. Even the coldest regions of protostellar disks, as we model them today, don't naturally produce objects with that extreme CO2 to water dominance. To get such a ratio, you need conditions so far outside the norm that they don't match any well-supported formation scenario. Yet the public line stayed the same. It's a comet, just an odd one. Next came size. Early estimates suggested a nucleus only a few kilometers wide, a small icy body that looked dramatic only because of dust around it. Those estimates were based on overall brightness, which is dangerous here because brightness is heavily boosted by the coma. When you try to subtract the coma's contribution, the remaining light implies a much larger nucleus. Some models put it near 20 kilometers across. Others, using Spherex infrared observations, allowed sizes up to about 46 kilometers. For scale, that is larger than Manhattan and far bigger than most comets we know. The mainstream response was to insist that nearly all the light must come from dust, not the solid core. But Hubble images showed the coma as diffuse rather than dense enough to explain that level of brightness on its own. Something doesn't add up. Then there's the orbit. An interstellar object entering the solar system should approach from a random direction at a random angle. The galaxy doesn't funnel visitors neatly into the plane of our planets. Yet Atlas arrived on a trajectory aligned within about 5 degrees of the ecliptic, right along the flat disk where the planets orbit. The probability of that alignment by chance was estimated around 0.2%, roughly 1 in 500, and it gets stranger. The timing and geometry of the path set Atlas up for close observational opportunities near Mars, Venus, Jupiter, and eventually Earth. The odds of that kind of best possible tour being accidental were argued to be around 0.5%, on the order of 1 in 20,000. One coincidence can happen. A chain of these starts to look engineered. Astronomers also reported subtle deviations from the predicted gravitational path. These are called non-gravitational accelerations. Comets can show them when jets of gas act like tiny thrusters. That's normal. What wasn't normal here was the magnitude and direction. The shifts were larger than expected for its presumed size and activity level, and not always aligned with sunlight-driven outgassing. The explanation offered was carbon dioxide jets, but CO2 jets should push material away from the sun and create tails in the anti-solar direction. Atlas showed a strong feature pointing sunward. No standard comet mechanism produces a stable jet aimed toward the sun. The coma itself raised another flag. In typical comets, outgassing is messy. Heating is uneven, jets are localized, and the coma is brighter on the sunward side. Atlas's coma appeared unusually symmetric and evenly balanced, as if material were being released in a regulated way rather than from chaotic patches of sublimation. Amateur observers noticed this first, and professional papers acknowledged it. But in public summaries, it was softened into unusual activity without serious follow-up. One of the sharpest anomalies came from nickel. Telescopes detected nickel vapor in Atlas's coma. Nickel in comets isn't the shock, the ratio is. In natural bodies, nickel and iron are produced and stored together. They show up together in asteroids, meteorites, and comet nuclei. Atlas was releasing nickel without the corresponding iron signal. To separate those two in nature is extremely hard. On Earth, we only do it through industrial refining. The pattern of nickel emission looked closer to what you would expect from refined material than from a raw rubble pile nucleus. Scientists floated exotic chemical pathways, interstellar weathering, cosmic ray processing, but these were speculative and untested. Light polarization measurements added a quieter but serious concern. Atlas showed extreme negative polarization, a specific orientation pattern in reflected light. Natural dusty surfaces usually yield positive or neutral polarization. Negative polarization at this level is associated with smooth, highly reflective, metallic surfaces or engineered materials. The effect was noted in technical work, then filed away as another oddity without a convincing mechanism. So by late summer 2025, we already had a short list of hard contradictions: composition dominated by CO2, size estimates that swing from tiny to tens of kilometers, an ecliptic aligned path with improbable flyby timing, sunward jets, symmetric coma behavior, nickel without iron, and polarization that doesn't behave like dust. Any one of these might be explained away. The problem is the pile. When the anomalies cluster, you don't get to wave them off independently. You have to explain why this single interstellar visitor is breaking so many normal rules at once. And that's where the story gets tense. Because the calmer the public narrative stays, the more the raw data pushes the other way. We are looking at an object that is either the strangest natural comet ever observed, or something our current categories aren't prepared to describe. Either way, the next pieces of evidence matter, because 3i Atlas is still inbound, still active, and still giving us new numbers to check against the official story. As Atlas kept approaching, the observation campaign widened. Ground-based telescopes tracked its brightness night after night, while space instruments watched in infrared and ultraviolet. If the object were a normal comet, its behavior should have settled into familiar patterns. A predictable rise in activity as sunlight warmed the surface, outgassing driven mostly by water, and a tail geometry that follows well-tested physics. Instead, the curve never really locked in. Models that fit 1 week of data would fall apart the next. The deeper the tracking went, the more Atlas seemed to be running on a different rulebook. One of the first surprises was the way its light changed over time. Comets spin, and that spin creates a repeating brightness variation called a light curve. For typical nuclei, the period emerges fairly quickly. With Atlas, different teams reported different values depending on which data slice they used. Some analyses pointed to a rotation period near 16.8 hours. Others suggested a longer and less stable cycle. That mismatch could be dismissed as observational noise if the object were faint, but Atlas was bright enough for good photometry. The more plausible interpretation was that the brightness wasn't controlled by a steady rotating core alone. Something else was modulating the light, either changing activity patterns or a physical structure that didn't behave like a single solid nucleus. A comet with a simple rigid spin should not keep producing incompatible period solutions. Then came the shape problem. High-resolution imaging never resolved a clear nucleus, but the coma's geometry allowed inference. The pattern of dust release implied a body that was either unusually elongated or surrounded by a structured envelope. Again, neither option fits comfortably into ordinary interstellar comet. An elongated nucleus is possible, but then rotational stability becomes an issue. A very stretched body spinning fast should shed material or fragment. Yet Atlas showed no obvious breakup signatures. The alternative is that the coma itself was organized, not just a messy cloud, but a kind of controlled outflow that maintained coherence over many days. Natural jets usually drift as the nucleus turns. Atlas's dominant features held direction too consistently. The dust was another clue. Spectra and polarization suggested the particles were not the fluffy carbon-rich grains seen in most comets. The distribution leaned toward larger, more reflective grains. Some observers described the scattering as closer to silicate-rich or even metallic dust. If that is correct, it deepens the nickel anomaly rather than explaining it away. Metallic or refinement-like signatures showing up in both gas and dust push you toward a picture that is hard to get from raw interstellar ice alone. At the same time, the ratio of gas production to dust production stayed strange. In a normal comet, higher gas output drags more dust with it, and the two rise together as the object warms. Atlas produced huge amounts of CO2 without a proportional dust surge. That means the gas was escaping in a way that did not efficiently loft surface material. There are only a few ways to do that. One is that gas is coming from deeper layers through vents rather than broadly sublimating at the surface. Another is that the surface is unusually strong or sealed, limiting dust entrainment. Both scenarios demand an internal structure that is not typical of loosely packed cometary rubble. The thermal story also didn't behave. Infrared readings suggested the surface temperature distribution was more uniform than expected. Most small bodies heat unevenly because rotation and surface texture create hot and cold patches. Uniformity implies either an unusually high thermal conductivity, meaning heat spreads quickly through the material, or a surface layer that is actively regulating temperature by continuous venting. High conductivity again points toward dense or metallic content. Regulation by venting points toward a system that is not random but persistent. Another issue was the timing of activity. Atlas became strongly active earlier than models predicted for its distance from the Sun. Water-driven activity should ramp up closer in, when solar flux is high enough to sublimate ice efficiently. CO2 can sublimate farther out, but the observed intensity still exceeded typical expectations. If Atlas were a CO2-heavy comet, it should still follow CO2 physics. Yet the outgassing rate was too high for the estimated surface area unless the activity was concentrated in powerful vents. That brings the conversation back to the same uncomfortable place: a small number of strong, stable jets rather than widespread, chaotic sublimation. Those jets also appeared to react weakly to changes in solar angle. In normal comets, as the object rotates, different areas heat up and jets brighten or fade. Atlas's main emission features did not track that cycle cleanly. Observers on different continents reported similar coma structures even when the viewing geometry changed. That consistency suggests either a near pole-on rotation, which would keep one hemisphere facing the Sun, or a source mechanism that is not sensitive to sunlight in the standard way. A pole-on orientation is possible but statistically not favoured, and even if it were pole-on, the earlier problems about size, composition, and symmetry remain. Supporters of the natural comet framing emphasize that interstellar objects might simply be far more diverse than what we see at home. That is a fair point in principle. Interstellar space should deliver bodies born under many different conditions, around many different stars. Diversity is expected. The problem with Atlas is not diversity, it's coherence across anomalies. Nearly every weird measurement points in the same direction. Atlas is chemically abnormal, structurally organized, and dynamically inconsistent with a fragile, porous ice ball. The most volatile part of the discussion was not about whether the object is artificial. It was about how carefully the public narrative was being shaped. In technical channels, many of these anomalies were openly listed. In public statements, the tone stayed fixed on reassurance. Terms like unusual or rare replaced more precise descriptions. Contradictory size estimates were treated as if they converged. The orbital coincidences were labelled interesting rather than improbable. The CO2 dominance was presented as a curiosity rather than a category breaker. That gap between data and messaging is what keeps the story alive. Because there is another layer here that doesn't depend on interpretation. Atlas is coming in on a timescale that allows future checks. Its distance will shrink. Its brightness will climb. Its interaction with solar radiation will intensify. If it is a comet, its behavior should become easier to model as more data arrives. If it is not, the mismatch should grow sharper. In the next stage of the approach, the object moves into regions where our instruments get much higher precision. The question is not whether Atlas looks dramatic. It already does. The question is whether the upcoming measurements force a clear choice between two possibilities: an unknown but natural category of interstellar body, or a structure that cannot be explained within comet physics at all. What happens next is where the story stops being a list of anomalies and becomes a test of what we think the solar system can admit. As Atlas crossed deeper into the inner solar system, the observation geometry tightened. The object became brighter, the coma grew denser, and the tails, plural, became easier to separate in different wavelengths. Under normal comet rules, this phase should be the most legible one. The closer a comet gets, the more strongly sunlight determines everything: heating, sublimation, dust release, and the direction of outflow. If earlier oddities were due to sparse data, they should start smoothing out now. Instead, several measurements sharpened into clearer contradictions. The first was the tail structure. In visible light, Atlas showed a dust tail as expected. But in infrared and certain narrow spectral bands, there appeared an additional component that behaved more like a gas or ion feature, yet it did not align cleanly with standard anti-solar geometry. Comet tails typically point away from the sun because gas and dust are pushed outward by radiation pressure and solar wind. Atlas kept presenting a persistent, bright feature closer to the sunward side that did not dissolve quickly. If that were a short-lived jet, it should swing with rotation or fade as illumination changed. It did not. That stability forced analysts to consider either an unusual internal vent system or a geometry that was somehow locked. At the same time, the non-gravitational acceleration became easier to measure. The higher the signal, the more tightly you can fit the orbit and see the residual drift. The residuals did not vanish, they grew more coherent. The acceleration direction stayed inconsistent with what you'd expect from CO2 sublimation alone. If CO2 were the driver, the strongest push should follow the thermal gradient created by sunlight. But the measured drift often implied thrust components not aligned with a simple dayside jet. In practice, that means one of two things. Either the activity is coming out in a configuration we don't see in normal comets, or something besides outgassing is influencing the path. A related clue sits in the momentum budget. To produce the observed acceleration with gas, you need a certain total mass of material leaving the nucleus per unit time. When you calculate that mass using the observed CO2 production rates, the numbers still don't close unless you assume unusually efficient collimation, narrow high-velocity jets rather than broad diffuse escape. But narrow jets should leave visible imprints, corkscrew patterns in the coma, rotating fans, or sharply defined sources. Atlas's coma remained smooth and symmetric overall. It looked like a body releasing gas in a controlled way, without the messy optical signatures that normally come with concentrated vents. Then there's the question of how the surface survives. A weak porous comet bombarded by strong CO2 jets should erode quickly. You'd expect a noticeable change in brightness slope, shifts in jet patterns, or outright fragmentation. Yet Atlas held together and stayed photometrically steady in a way that suggests mechanical strength. That strength is hard to reconcile with a nucleus that is mostly volatile-rich ice and dust. Strong cohesion implies either an unusually compact sintered interior or a surface layer capable of resisting high internal pressures. Either option is far from standard comets, especially interstellar ones that should have been battered for millions of years in deep space. Around this time, some teams looked for a companion object or a fragment trail. Interstellar comets could arrive as loosely bound pairs or with leftover debris. The searches didn't reveal a clear secondary nucleus. That absence matters because it argues against a recent breakup scenario that might have explained the light curve instability and the size confusion. If Atlas were a fresh fragment, many of the earlier disagreements would make sense. But the body behaved like a single intact object. The chemistry also stayed extreme. The CO2 dominance did not fade as the object warmed. A common expectation for a CO2-rich comet is that water activity eventually catches up closer to the Sun. That didn't happen in the ratios that were observed. Water increased, yes, but never approached dominance. The simplest reading is that there is genuinely little water available to sublimate. That points to a formation path that stripped water preferentially or locked it in a form that doesn't escape easily. Both ideas are difficult to support with current interstellar body models. If a natural object arrives with almost no water as it heats, it challenges what we think is chemically stable over interstellar travel. Another subtle detail was the evolution of particle sizes in the dust tail. In most comets, smaller grains dominate early activity, then larger grains become more common as surface layers erode. Atlas showed the opposite tendency. The scattering hints suggested a persistent population of relatively large, reflective grains from the start, with no strong drift toward finer material later. That looks less like erosion of fragile surface regolith and more like continued release from a structured source region. Again, you can force a natural explanation, but each natural explanation has to be unusually specific. This is also the stage where comparisons to the previous interstellar visitors became pressing. The first interstellar object we confirmed, Oumuamua, lacked a clear coma but showed strong non-gravitational acceleration. The second, Borisov, looked far more like an ordinary comet. Atlas did not sit comfortably between them. It combined traits from both in a way that made it harder to classify. It had a bright coma like Borisov, but accelerations closer to the puzzle of Oumuamua. It was chemically more alien than either, and its orbit was more conveniently aligned than a random galaxy delivery should allow. That mixed profile is why the scientific tension around Atlas steadily rose even as public messaging stayed calm. There is also a practical reason why the tone stayed careful. At this distance, Atlas became a target for radar attempts and high-precision astrometry, but the object was still too far for definitive surface imaging. That gap is dangerous for interpretation. If you speculate too hard and the next round of data normalizes the picture, you look reckless. If you stay too conservative and the data becomes stranger, you look like you were minimizing a real anomaly flow. So the community held position, publish the numbers, avoid the framing battles, and wait for closer passes. But the numbers we already have are enough to outline the dilemma. A purely natural explanation needs Atlas to be a large, mechanically strong nucleus, almost water poor. CO2 dominated even under intense heating, capable of producing well-collimated thrust without messy optical signatures, and delivered on a trajectory improbably aligned with the ecliptic and with multiple observationally convenient encounters. That is a long list of specific requirements for one object. Occam's razor doesn't forbid rare things. It just asks whether the rarity is still compatible with our base assumptions. As Atlas heads toward its closest approaches, the stakes shift from interpretation to prediction. Natural comet models make clear forecasts about how gas ratios should evolve, how the coma should respond to solar angle, and how the acceleration should scale with distance. If those forecasts fail in systematic ways, we will have to expand our categories. Not because we want a dramatic story, but because the object is forcing the expansion. For now, the trajectory continues inward. The next measurement window is the one that should decide whether the earlier anomalies were surface-level quirks, or whether Atlas is signaling a deeper mismatch with comet physics. If it behaves like a comet when the sun is at full strength, the story narrows. If it keeps refusing the rules, the story changes into something we haven't had to say out loud before. The closer Atlas got, the more the conversation shifted from "what is it" to "what can we test?" By this phase, the object was bright enough for coordinated monitoring across many instruments at once. That matters because most earlier ambiguity came from patchy coverage. Now the data streams overlapped. When multiple methods point to the same odd result, the explanation has to be more than measurement noise. One test focused on how the gas production scales with distance from the sun. For a comet, this scaling follows a recognizable pattern. The solar flux increases as the inverse square of distance, and sublimation rates rise accordingly. Different volatiles have different thresholds, but the overall curve still sits within a family of expected slopes. Atlas's CO2 production rose fast, but in a way that seemed decoupled from the expected heating curve. It didn't just increase, it surged in bursts that didn't match the smooth thermal ramp. Bursty activity can happen in comets, usually when fresh ice is exposed by landslides or cracking. The catch is that such outbursts leave visible scars in the coma. Sharp arcs, fragment clouds, or changes in the dust-to-gas ratio. Atlas showed bursts without the usual collateral mess. That inconsistency pushed analysts toward internal pressure models. In simple terms, imagine CO2 trapped under a surface layer that behaves more like a lid than loose dust. As heat penetrates, pressure builds until it vents through stable channels. This could explain bursts and collimated thrust. But it also creates a new problem. Repeated high-pressure venting should gradually widen channels, disrupt the surface, and change the outflow geometry. The long-term stability of Atlas's features suggests the vent system, if it exists, is self-maintaining. That is not impossible in nature, but it's not something we see often. Most comets evolve visibly as they heat. Another test involved looking for water-related radicals in the coma. Water doesn't only show up as H2O lines, it produces secondary species when sunlight breaks it apart. These radicals are common, bright, and easy to detect in normal comets. Atlas did show them, but at levels that consistently lagged behind what its total brightness would lead you to expect. The mismatch reinforced the view that water is not just secondary, but genuinely scarce in the active layer. If so, Atlas is not simply a comet with an odd ratio. It may be an object whose volatile inventory is dominated by a single species in a way that violates our default formation assumptions. A third test was about torque. Jets don't only push objects through space, they also twist them. Most active comets exhibit measurable changes in spin as their jets fire. A large body with strong jets should show even clearer torque signatures. Yet Atlas's rotational behavior stayed stubbornly ambiguous. The light curve never settled into a clean, long-lived period. Instead, it hinted at either a slowly changing spin state or a geometry that hides rotational modulation. If Atlas were being torqued by high-powered jets, we would expect its spin to drift in a detectable direction over weeks. The lack of a clear trend is hard to square with both strong jets and a simple rigid nucleus. Some propose that Atlas could be tumbling rather than rotating around a stable axis. Tumbling bodies do produce complex light curves, and Oumuamua is widely discussed in that context. But tumbling under strong asymmetric outgassing should damp into a simpler mode fairly quickly, or evolve into chaotic fragmentation. None of that appeared, so tumbling remains a possible explanation, but it carries extra baggage. It doesn't resolve the mechanical strength issue, the gas scaling issue, or the orbital coincidences. It only moves one puzzle piece without fitting the rest. At this stage, the directionality of dust release also became more informative. Observers tracked how dust fans evolved over several rotations. In normal comets, dust patterns broaden and shift because different surface patches turn into sunlight. Atlas's dust distribution stayed tightly correlated with the same few source regions. The regions looked persistent, almost fixed in object coordinates rather than drifting with illumination. That again suggests a small number of stable vents or nozzles that dominate activity. If that is the case, Atlas is not behaving like a porous ice rock assembly with widespread sublimation. It is behaving like a body with structured outlets. The photometric slope added another subtle clue. Beyond raw brightness, astronomers look at how brightness changes with phase angle, the angle between sun, object, and observer. Dusty comets show a characteristic phase behavior because dust grains scatter light in predictable ways. Atlas's phase curve leaned toward a higher backscatter component than typical dusty comets. That is consistent with larger, smoother, or more reflective particles. It doesn't prove anything alone, but it is consistent with the independent hints from polarization and dust spectra that the particulate environment is abnormal. A natural rebuttal remains. interstellar bodies might carry surface crusts altered by long exposure to galactic cosmic rays and interstellar chemistry. Such crusts could be stronger, less dusty, and more CO2-rich than solar system equivalents. That idea is worth taking seriously. The problem is that every time we invoke it for Atlas, we have to invoke it in a maximal form. The crust must be strong enough to bottle CO2 under pressure, clean enough to avoid dust entrainment, stable enough to maintain long-term vent geometry, and chemically skewed enough to suppress water even under intense heating. A modest crust doesn't get you there. A highly specific extreme crust might, but without a clear physical pathway, that remains a patch rather than a full explanation. Meanwhile, as Earth-based monitoring improved, the object's astrometric residuals were recalculated repeatedly. Each time the fits got better, the residual acceleration remained. Its magnitude scaled with distance in a roughly comet-like way at first, but the vector kept small systematic offsets from the anti-solar direction. In other words, Atlas was being pushed in a broadly thermal regime, but not precisely as an unstructured comet should be. The push looked steered, not random. That word can be misleading, so keep it literal. The direction was too stable relative to the object's orientation, and too resistant to the normal jitter we see in natural jets. This is also where the risk conversation, the practical one, started showing up quietly in professional circles. Not risk of impact, because nothing in the orbital solutions suggested a collision with Earth. The risk was interpretive and procedural. If Atlas is a natural outlier, we need to understand the mechanism because it changes our models of what interstellar bodies can be. If it is not natural, we need to recognize that possibility early enough to study it properly. In both cases, minimizing anomalies too hard would be a mistake. The correct posture is not panic, but pressure testing. The approach continued. With each week, the object became less a distant mystery and more a local physical system we could track in detail. And the more it was tracked, the tighter the anomaly cluster became. Atlas was not drifting toward normality. It was drifting toward clarity in its weirdness. The next window is crucial because it brings Atlas into conditions where water-based activity, if it exists in meaningful amounts, should finally assert itself. If the object suddenly pivots into a standard comet profile near peak solar heating, many earlier questions soften. If the CO2 dominance persists, if the structured jets hold, and if the acceleration vector stays offset, then we will have to accept that Atlas sits outside the current comet family in a more fundamental way. Either path is informative. Only one path keeps the word ordinary on the table. By the time Atlas neared the region where solar heating reaches its most intense regime, the object had already forced a shift in how it was being modelled. Early on, analysts could still treat its anomalies as separate curiosities. Now the anomalies were interacting. The chemical imbalance affected the outgassing physics. The outgassing physics affected the acceleration. The acceleration fed back into size estimates because thrust depends on surface area and mass. When you ran a model that tried to satisfy one constraint, it immediately strained another. That kind of tension is exactly what you see when an object belongs to a category you have not fully described yet. At these distances, a standard comet should show a clear transition. Water sublimation turns on strongly, dust lofting becomes more efficient, and the coma shifts toward a brighter, more chaotic sunward side. The tail geometry also becomes cleaner. Dust tail pushed outward by radiation pressure, ion tail shaped by the solar wind plasma field, both reliably anti-solar. The closer Atlas got, the more carefully observers looked for that transition. The transition did not arrive in a normal way. Waterline strengthened, but the overall activity remained dominated by carbon dioxide. Even under near-peak solar input, the CO2 to H2O ratio stayed heavily skewed. That is not just unusual. It implies that either Atlas simply carries very little accessible water, or the water is trapped in a matrix that does not open under heating the way cometary ice normally does. The first possibility is chemically hard to explain for a body that should have formed in an environment where water ice is one of the most stable and abundant condensates. The second requires an internal structure that blocks diffusion to the surface, even while CO2 escapes freely. Both are extreme configurations. The dust response kept matching that odd chemistry. If CO2 jets were firing through stable vents under a sealed surface, you would still expect dust to rise more steeply once the thermal wave reached deeper, more water-rich layers, because deeper layers should be less consolidated and easier to erode. But the dust production stayed comparatively flat relative to gas. Atlas looked like it was venting volatiles through narrow pathways without tearing up the surrounding material. That is a hallmark of a mechanically competent shell, not a loose aggregate. This is where the internal density question became unavoidable. If the object's mass were low, strong jets would push it more than observed. If its mass were high, then to get the observed acceleration you need even stronger jets, which should leave clearer optical signatures. The simplest way to balance those terms is to assume a denser than normal nucleus with concentrated, efficient thrust. Dense nuclei exist in nature, but they are not typical for comets, and they are even less typical for comets that have spent long epochs in interstellar space. Long exposure usually makes outer layers brittle and devolatilized, not mechanically robust. Another line of reasoning focused on survivability. Atlas was receiving a level of solar energy that should drive visible evolution in a volatile-dominated body. Many comets brighten dramatically, then lose symmetry, then develop multiple jets as new areas warm. Some shed fragments or show spurts of dust as surface layers fail. Atlas, by contrast, held its activity geometry for a long stretch. It did not evolve toward disorder. It maintained a small number of strong, stable sources. This is not impossible for a comet with a special spin axis and a special vent layout. But again, the explanation has to be special in multiple independent ways at once. At this point, the orbit alignment became more than a statistical oddity. With refined astrometry, Atlas's incoming trajectory remained tightly in the ecliptic neighborhood. The more accurate the numbers got, the less room there was to say the alignment was an artifact of early uncertainty. Interstellar objects should arrive with a wide distribution of inclinations, and most should be far from the ecliptic plane. An ecliptic-aligned arrival is not forbidden. It is just improbable. When you place that improbability beside the other improbabilities, you cannot treat it as background noise. The path also continued to be observationally convenient in a way that was hard to ignore. Atlas stayed within reachable angular windows for many assets across key time intervals. In practical terms, it gave us unusually long, uninterrupted viewing campaigns at precisely the distances where the strongest diagnostics turn on. A natural interstellar body could do this by chance. But chance is not a mechanism. The question is whether chance is still the best explanation when convenience stacks atop chemistry, dynamics, and structure. None of this means the object had to be artificial. The scientific community is careful about that word for good reasons. Artificiality is an extraordinary claim, and nature is fully capable of producing things we have not seen before. The point is simpler. If you want a natural explanation, it has to be a natural explanation that simultaneously accounts for all the coupled constraints, not just one at a time. One proposal was that Atlas could be a fragment of a differentiated parent body. Imagine a larger icy planetesimal that partially melted or chemically separated early in its history, then was disrupted, and one fragment was ejected into interstellar space. A fragment from a CO2-rich layer with unusual mechanical strength could, in principle, reproduce some of the chemistry and density hints. But that still leaves the lack of iron with nickel, the stable sunward feature, and the persistent offset acceleration vector. Differentiation doesn't naturally isolate nickel from iron without leaving a broader suite of metal signals. It also doesn't explain why the outflow geometry stays so regulated. Another proposal invoked extreme cosmic ray processing. Over millions of years, energetic particles can modify ice chemistry, drive radiolysis, and form a hardened crust. Such processing could deplete near-surface water and favor CO2 release. It could also increase mechanical strength. This is plausible as a general effect. The issue is scale. To push water down to a few percent while leaving CO2 as a dominant, easily vented volatile requires a degree of processing far above what models typically allow without also carbonizing or sealing the surface, to the point where gas cannot escape efficiently. In other words, the processing has to be both intense and selectively permissive. That combination is not well supported. A third proposal suggested that Atlas might have an internal reservoir of supervolatile compounds, driving activity from the inside, with CO2 acting as the observable proxy. If subterranean volatiles are heated and escape through a small number of conduits, you could get collimated jets and bursts. But internal reservoir models generally predict strong torque effects and rapid change over time as pressure pathways open and collapse. Atlas's long-term stability again pushes against that expectation, so the modelling space narrowed. Each attempt to keep Atlas inside normal comet physics required layers of special pleading, and those layers began to conflict with each other. A thick crust helps explain dust suppression, but it fights against the need to vent huge CO2 flux. A dense nucleus helps reconcile thrust and stability, but it fights against the expectation that comets are low density and porous. Stable vents help explain the smooth coma, but they fight against the lack of torque-driven spin evolution. You can fix one issue, but you pay for it with another. The rational response to that kind of model tension is to ask whether the object is a comet at all, not in a sensational way, but in a taxonomic way. Our categories are built from solar system examples. Interstellar bodies might be fundamentally different in internal layering, chemistry, and surface physics. Atlas could be telling us that the comet label is too narrow. A CO2-dominated, mechanically strong, vent-structured interstellar body might be a real class that we have never sampled before. If so, it forces new questions about how planetary systems form volatiles, how ejection works, and what survives interstellar travel. There is a second possibility that remains low probability but cannot be logically excluded from the evidence set. If a body behaves like it has dense structure, stable nozzles, reflective or metallic particulate signatures, and a thrust vector that stays unusually coherent, then one of the possible explanations is technological origin. That does not mean it is true. It means it is on the list of hypotheses that must be tested rather than suppressed. In science, you do not choose which hypotheses feel comfortable. You choose which ones survive predictions. Those predictions are now clear. If Atlas is a new natural class, its gas ratios should remain CO2 heavy, but still respond smoothly to solar distance. Its acceleration should scale with production rates and show some stochastic drift as vents evolve. Its coma should eventually show morphological change as thermal waves reach new layers. If Atlas is technological, you would expect coherence to persist or even sharpen, thrust vectors staying stable beyond what jets allow, activity staying regulated despite heating, and spectral signatures continuing to show refined separations rather than bulk, correlated abundances. The object keeps moving inward. The closer it gets, the less room there is for interpretation by analogy, and the more the explanation has to meet direct quantitative tests. Atlas has already told us that the solar system is not just a place we observe. It is a laboratory where the galaxy occasionally drops in something that forces us to expand the map. Whether that expansion is a new natural category or something even stranger is what the next phase will decide. As Atlas moved through its most informative observational corridor, a quiet shift happened in how the object was discussed among specialists. The focus stopped being purely descriptive. It became comparative and predictive. People began asking not just, is it weird, but how weird compared to the full range of natural bodies we already know. That matters because nature has a wide tolerance for oddities, but it also has patterns. When one object breaks too many patterns at once, you either discover a new natural class or you admit that your first label was wrong. A simple way to frame this is to look at the three interstellar visitors as a set. The first, one Oumuamua, had no obvious coma, but showed measurable non-gravitational acceleration and an unusually high reflectivity. The second, 2I Borisov, behaved like a classic comet with water-rich outgassing and a very familiar dust tail. Atlas arrived as a hybrid that does not sit on a clean spectrum between those two. It combines a strong coma like Borisov with acceleration behavior closer in spirit to Oumuamua. But it does so with a chemistry profile more extreme than either. If the interstellar population is simply diverse, you would expect the third object to add a new flavor, not to fuse the hardest puzzles of the prior two into one case. Another comparison comes from the distribution of volatile ratios. Within our solar system, comets can vary a lot, but those variations sit in a statistical envelope. Water remains dominant in active layers. CO2 can be high in some objects, especially at larger heliocentric distances, but it rarely overwhelms water at close approach. There are comets labelled Ko-rich or CO2-rich, yet even those do not approach a 95-5 split under strong solar heating. Atlas did. To treat that as a normal tale of the distribution, you would need to argue that interstellar bodies are not just more varied, but fundamentally shifted in their chemistry to the point where water-poor objects are common. That is possible. It would also be a major update to our models of protoplanetary disks, because water ice is one of the easiest solids to form and preserve. If interstellar chemistry is that different, Atlas is not a curiosity. It is a calibration point for planet formation itself. There is also a comparative geometry puzzle. The ecliptic plane alignment is not just a statistical note. It affects what kinds of natural delivery processes are plausible. An interstellar object arriving close to the ecliptic could, in principle, be the result of gravitational focusing through the solar system's motion relative to the local stellar neighborhood. But focusing does not preferentially flatten trajectories to within a few degrees of the planetary plane. It tends to bias directions relative to the Sun's motion, not to the planet's orbit disk. So the alignment serves as a constraint. If a natural mechanism is invoked, it must be a mechanism that couples galactic kinematics to a planetary plane. Right now, that coupling is not part of standard dynamics. The same is true for the sequence of favorable viewing encounters. The more you study the resulting geometry, the harder it is to see it as a single random draw. The object's path not only stayed accessible for long campaigns, it did so during precisely the windows that maximize chemical diagnosis and acceleration fitting. A random interstellar passerby usually gives you a short, messy arc of data. Atlas gave a long, clean arc through the most diagnostically rich region. That does not prove intent. It proves that chance, if it is the explanation, is doing a lot of work. At this point, prediction tests became central. If Atlas is a natural body driven by CO2, then near and after perihelion, its activity should show a few things. First, the CO2 production should peak and then drop smoothly with distance. Second, the dust production should lag behind gas, but eventually rise as thermal waves reach deeper material. Third, the acceleration vector should become less coherent over time as vents evolve and the surface changes. Fourth, the coma morphology should broaden and drift as new active regions turn on. These are not arbitrary expectations. They follow from how volatile rich bodies respond to a fast, rising thermal gradient. The early perihelion data did not convincingly show that pattern. The CO2 output remained high and stable. Dust production did not surge in a proportionate way. The acceleration vector did not randomize the way multi-event natural systems usually do. The coma morphology stayed organized longer than expected. None of these alone is a knockout. The tension comes from their combination being stable across multiple epochs. One more line of evidence involved the way Atlas responded to micro-variations in solar input. Sunlight is not constant. The solar wind changes, ultraviolet flux fluctuates, and these shifts are often reflected in cometary activity within days. When analysts stacked data by solar conditions, Atlas showed weaker coupling than normal. Its activity was not fully insensitive, but it did not track solar variability with the same immediacy you see in typical outgassing. That suggests a buffering layer between external heating and internal release. In plain terms, the system looked regulated rather than directly driven. Regulation can still be natural. A thick crust with a network of channels can damp external variability. But again, to make regulation strong enough to explain Atlas, while also allowing massive CO2 flux, you need a structure that is both highly insulating and highly permeable in specific directions. That is a tight design requirement for a natural object. Another prediction test concerns post-perihelion evolution. Many comets reveal their internal heterogeneity after peak heating. The surface collapses in places, new vents open, dust jets change direction, and gas ratios shift as different layers get exposed. If Atlas is natural, the period after closest approach should be where the system finally becomes messy. If that messiness fails to appear, then the idea of a chaotic, porous nucleus weakens further. There is also the longer-term question of what Atlas will look like once it exits. If it is a fragile interstellar comet, intense solar heating should strip volatiles and leave a darker, less active remnant. Its brightness should drop faster than a purely geometric retreat. If it is a dense, crusted, or engineered body, the decline could be slower or controlled. The exit phase is slower in information to arrive, but it is actually a powerful discriminant. It tells you whether the activity was a transient skin effect or a persistent system. All of this sets up a simple reality. Atlas is no longer just a name in a catalogue. It is an active test object for our understanding of interstellar visitors. The evidence so far says it behaves like a body with strong internal coherence. It vents huge CO2 through stable outlets. It resists surface disruption. It carries particulate and gas signatures that lean away from raw, mixed, primitive material. And it arrived with a geometry that is hard to call typical. If that coherence breaks in the next stages, if new vents appear, dust surges, ratios drift toward water-rich behavior, and acceleration starts jittering, then the case narrows toward an extreme but natural interstellar comet. If the coherence persists, we do not get to keep calling it ordinary. We have to either name a new natural class with a convincing formation pathway, or keep the technological hypothesis on the table until the predictive checks rule it out. The story is not about choosing a dramatic answer. It is about respecting the logic of the measurements. Atlas is forcing that logic into a corner. The next data points will determine whether we step out of that corner by expanding comet physics, or by admitting that the object never belonged to comet physics in the first place. What makes Atlas difficult is not that it is mysterious in a poetic sense. It is difficult in a mechanical sense. You can write down the equations for outgassing, thrust, heating, dust entrainment, and orbital drift. Then you try to fit the observed values. With ordinary comets, the fit is never perfect, but it is stable. With Atlas, the fit stays unstable unless you push multiple parameters to extreme edges at the same time. That is why the discussion keeps returning to internal structure. Internal structure shows up indirectly through how energy moves. In a porous comet, heat penetrates slowly. You get a shallow active layer and the rest stays cold. Activity migrates as the surface erodes. In a denser body, heat spreads more efficiently. That can keep activity localized and stable because the same reservoir stays warmed through time. The infrared behavior of Atlas leans toward the second picture. Its thermal response suggests that whatever is driving CO2 release is not a thin, fragile skin. It behaves more like a deeper system connected to the surface through persistent channels. Those channels, if natural, create a strong constraint on history. To sustain stable, high-flux vents, Atlas must have formed with internal voids or fractures that survived ejection from its home system and a long interstellar cruise. Ejection events are violent. They expose bodies to shocks and tidal stresses. Many interstellar fragments should arrive cracked, irregular, and structurally weakened. Atlas does not look structurally weakened. Either its material was tough enough to endure the journey without losing its vent architecture, or its vent architecture is not simply inherited damage, but something more resilient. A related clue is how little rotational evolution we see. Stable vents pushing hard should spin the object up or down. Even if a single vent dominates, the torque adds up over weeks. Yet the rotational signatures remain muted. The simplest way for torque to stay small is if thrust vectors are arranged so they partly cancel, or if the vents sit near the spin axis. Both arrangements can exist in nature, but neither is likely to appear by accident in a body that also needs to explain the other anomalies. The more constraints you stack, the less random chance can carry the load. This is where the geometric and mechanical stories intersect. A comet that is venting in one or two stable places is most strongly constrained by its axis orientation. The entire activity profile then depends on where the Sun sits relative to that axis. If Atlas is doing this naturally, it requires a specific spin state that keeps the same vent geometry sunlit across a long stretch. That spin state is not impossible. It is simply another specific requirement on top of many others. One way to loosen those requirements is to assume Atlas is not a single homogeneous nucleus. It could be a contact binary, two lobes gently fused, or a rubble body wrapped in a hard crust. Those configurations can produce complex light curves and unusual activity distributions. But they also tend to reveal themselves with evolving coma patterns and changing jets as different surfaces heat. Atlas still behaves more uniform than those models normally predict. You can keep adding structure to a natural model, but each added trick makes the model more fragile unless it also explains multiple observations at once. Another line of reasoning looks at what kind of parent environment could create a CO2-dominated body. In standard disk chemistry, CO2 is abundant, but usually not more abundant than water ice. To make CO2 dominant, you need either a region where water is depleted or a process that reworks water into other species while preserving CO2. Water depletion can happen close to the parent star, but close-in regions also tend to be warm enough to prevent CO2 from freezing efficiently. Farther out, CO2 freezes easily, but water freezes even more easily and stays plentiful. So a pure formation argument struggles. That pushes you toward transformation history. Maybe Atlas started water-rich, then water was preferentially lost. Water can be removed by repeated heating cycles or by radiolysis that breaks it into hydrogen and oxygen, with hydrogen escaping more easily. Over very long times, interstellar processing could shift the volatile balance. But again, if processing is strong enough to erase almost all accessible water, we should also expect other deep chemical changes, including heavier organic residues and altered dust properties in a way that is easy to identify. Atlas does show altered dust properties, but not the full suite you would predict from a near-total water erasure. The transformation story helps a little, but not enough. There is also a dynamical angle that doesn't get discussed much in public. Interstellar objects arrive with some velocity relative to the Sun. That velocity defines their hyperbolic excess speed, and it places them on a distribution shaped by galactic stellar dynamics. Atlas's inbound speed sits comfortably within the expected interstellar range, so there is nothing exotic there. The exotic part is the inbound direction relative to the solar system's plane. If you remove all other context, you would call that a rare alignment and move on. With the rest of the context in place, it becomes part of a structural pattern. Atlas looks like it is interacting with the solar system in a way that maximizes both detectability and stability. That is why some researchers frame the object as a stress test rather than a riddle. If it is natural, it stretches our comet and disk chemistry models. If it is not natural, it stretches our assumptions about what the solar system might encounter. Either way, the right approach is the same. Treat the object like a system with competing hypotheses and let data decide. In practice, that means watching for breaking points. Natural systems break in predictable ways. A volatile body near the Sun tends to become less symmetric, not more. Jets tend to spawn secondary jets as fresh ice appears. Gas ratios tend to drift as layers are exposed. Acceleration vectors tend to wander as thrust sources change. If those breaking points show up post-perihelion, the natural case strengthens rapidly. If they do not, the natural case must evolve into a new class with a fully worked physical pathway, not just a list of special exceptions. So the story enters its most decisive phase. Atlas has already given us the anomalies. Now it is giving us a timeline. The next part of the track is where either natural disorder finally appears, or coherence persists past the point where comet physics can comfortably hold it. After perihelion, most comets begin to reveal what they really are. The peak heating phase acts like a stress test. If the nucleus is porous and volatile rich, the surface changes quickly. Old vents collapse, new ones open. Dust production often spikes late, and the coma loses its earlier symmetry. Even comets that look restrained on the way in tend to become visibly messier on the way out. That is the normal direction of evolution. Atlas was expected to follow that direction if it were a natural body driven by volatile physics. The first post-perihelion datasets did not show a clean break into disorder. Activity levels dropped, but they dropped in a controlled way. CO2 production stayed dominant longer than expected. The decline curve was not the steep fall you see when a small active layer gets exhausted. It looked more like a reservoir maintaining output and then gradually throttling down. Again, regulation is not impossible in nature, but it is not typical for comets that have just gone through maximum solar stress. The coma geometry also stayed stable longer than the inbound models anticipated. Instead of a chaotic spread of secondary jets, the same major sources continued to shape the dust and gas envelope. The overall brightness weakened, but the structure did not fragment into multiple competing outflows. In a natural scenario, that implies either that the active system is confined to a few deep vents that survived perihelion without widening or collapsing, or that the accessible volatile inventory is narrowly concentrated and insulated from surface disruption. Either way, you are dealing with a body whose internal plumbing behaves as a durable subsystem, not a fragile surface phenomenon. The dust-to-gas ratio remained low. This is useful because post-perihelion is when dust often catches up. As thermal waves reach deeper layers, dust gets lofted more efficiently and tails broaden. Atlas did not show a late dust surge that would indicate new terrain becoming exposed. The dust tail weakened with gas in near lockstep, preserving the same unusual coupling seen on approach. A sealed or mechanically tough surface can explain this, but only if that surface can keep resisting erosion while still allowing strong gas throughput for months. There is a narrow band of natural materials that can do both, and they are not the standard comet mix. Rotational behavior stayed unresolved in a way that is itself informative. If perihelion outgassing had significantly modified the body, the light curve should simplify after the most violent stage ends. Many comets show clearer periodicity as they move outward and activity calms. Atlas continued to resist a simple spin solution. That could still mean an awkward viewing geometry. It could mean tumbling. But the persistence of ambiguity after the largest torque episode makes the strong asymmetric jets on a simple rigid body picture even harder to keep. There is another effect that becomes diagnostic on the outbound leg, the memory of the surface. When a comet loses volatiles, the surface darkens and activity shifts to fewer regions. Spectral slopes change. Reflectivity tends to drop as dust mantles build. Atlas's photometric behavior did not show a dramatic darkening trend. The surface, as inferred through the coma and phase curve, stayed on the reflective end of what comet dust usually yields. This supports the earlier hints that its particulate environment is not dominated by fluffy dark grains. It suggests either a mineralogy richer in reflective silicates or a contribution from smoother, higher albedo material. If you gather all post-perihelion signals together, you get a consistent picture. Atlas did not behave like a body that was running out of fragile surface ice. It behaved like a system with internal reserves that can keep releasing CO2 through stable outlets without shredding the surface or switching on a swarm of new vents. That is a strong statement. It is also testable against what we see in natural solar system objects. The closest analogues in our own system are not comets, but a subset of so-called transitional bodies. Objects that have comet-like orbits but asteroid-like structure, or asteroids that show limited regulated activity. Some of these bodies vent volatiles through fissures while remaining mechanically robust. Their activity can be stable and dust-poor. But even these cases are mostly water-driven, not CO2-dominated, and their active signatures are weak compared to Atlas. If Atlas belongs to an interstellar version of that class, then we are looking at a natural type we have never known existed. The alternative hypothesis, still low probability but not erased by the outbound data, is that Atlas is engineered or at least shaped by processes that mimic engineering. The outbound behavior is relevant because engineered systems are designed to maintain coherence under stress. A natural comet is not. If coherence persists past perihelion without the expected chaos, that does not prove design. It simply removes one of the easiest natural exit routes. So the problem narrows to a choice between two expansions. Either we expand natural categories by accepting that interstellar space can deliver mechanically strong CO2-dominated, vent-regulated bodies that stay coherent through perihelion, or we accept that there are other classes of objects that can enter the solar system and mimic comet activity in a controlled way. Both expansions are uncomfortable. The data does not care which one feels safer. The outbound leg continues to provide slower, cleaner tests. As Atlas retreats, its activity should eventually drop below detection thresholds. If it is natural, the drop should reflect exhaustion of accessible CO2 reservoirs, and the remaining body should behave like an inert remnant. If activity persists longer than its volatile inventory allows, or if thrust effects remain measurable even as gas lines fade, then the simplest natural energy budget fails. That is the last hard boundary any hypothesis must respect. For now, Atlas is still bright enough to track, still active enough to model, and still coherent enough to keep its anomaly set intact. The story is no longer about surprise. It is about resolution. Either this object forces a new chapter in interstellar body physics, or it forces a different kind of chapter entirely. The next decline phase, quiet as it looks, may tell us more than the approach ever could. As Atlas kept fading on its way out, the science shifted into a slower, colder kind of clarity. When an object is bright and loud, you can argue about interpretation. When it is dim and quiet, the argument has to fit budgets, energy, mass, and time. That stage is where many exotic stories die, because nature has limits you can calculate. The central budget here is simple. If the acceleration is caused by outgassing, then the thrust must be tied to the amount of gas leaving the nucleus. As Atlas retreats and solar heating weakens, CO2 production should fall, and any non-gravitational acceleration should fall with it in a predictable way. The decline does not have to be perfectly smooth. Natural vents can sputter, but the overall relationship between gas output and orbital drift should stay tightly correlated. So far, Atlas has declined in brightness and activity, but not in the proportion expected for a fragile surface layer. The drop has been gradual, almost staged. That behaviour can still be natural, particularly if the CO2 source lies deeper than the skin and is connected to the surface through a stable fracture network. But if that is the case, the object must carry a significant internal CO2 reservoir, and it must be able to vent that reservoir without collapsing its channel system. In solar system comets, stable long-lived venting on a small number of outlets is rare. In interstellar bodies which should be more processed and mechanically stressed, it is rarer still. The outbound data does not rule out the scenario. It just reinforces how specialized it would have to be. At the same time, the composition story is approaching its last meaningful checkpoint. When volatiles dwindle, the relative contributions of species can change. If water was present but trapped, then repeated heating across perihelion and outward should eventually open pathways for it to escape. If that happens, a late rise in water-related signatures would appear even as total activity falls. Atlas has not shown a convincing pivot toward water-dominant chemistry. The CO2 bias held through the peak and continued outward. That persistence implies the accessible inventory is genuinely CO2-centric, not just temporarily skewed. For a natural interstellar body, that is a strong constraint on origin. The dust behavior continues to match this view. If Atlas were gradually eroding a normal comet mix, dust grain sizes should drift toward finer, darker material as surface regolith breaks down. Instead, the scattering properties remain on the reflective side, and the large grain population does not collapse into a fine dust flood. That looks like material being released through limited channels rather than broad surface shedding. It also fits with the earlier implication of a mechanically coherent surface. This outbound trajectory also gives a chance to check whether a dead remnant emerges the way comet theory predicts. In a typical case, once outgassing falls below a threshold, the residual body behaves like a dark asteroid on a hyperbolic path. Any remaining acceleration becomes negligible. The coma becomes undetectable. The light curve is governed by rotation and phase angle alone. If Atlas crosses that threshold cleanly, it strengthens the view that we are dealing with an extreme but natural volatile system. If, however, measurable acceleration persists beyond the point where gas lines vanish into noise, then outgassing cannot be the single driver. There are only a few ways to explain continued thrust without detectable mass loss. One is that outgassing continues but through channels that produce little visible coma, essentially a low dust or highly collimated exhaust that is hard to see. Another is that radiation pressure or other non-gas forces are acting on an object with unusual area to mass ratios or surface properties. Such mechanisms were debated for Oumuamua. For Atlas, they would require a geometry or material response that remains coherent on retreat. Again, not impossible, just tightly constrained. At this point, the taxonomy question becomes unavoidable. even if you avoid any sensational frame. Comet is a label tied to water ice behavior, porous structure, and messy solar-driven activity. Atlas does not match that cluster. If it is natural, it is almost certainly not a comet in the solar system sense. It is a different interstellar volatile body, one that uses CO2 as its main working fluid and carries a surface strong enough to vent through stable outlets. That is already a new class, whether we call it one or not. Once you accept that, the remaining work is to ask how common such bodies might be. If Atlas is a rare tail event, then we learned that the interstellar population has wider chemistry and structure than expected, but still within a smooth distribution. If it is not rare, if CO2 dominant, mechanically durable interstellar bodies are common, then our sampling so far has been deceptive and our formation models need a larger overhaul. That question won't be answered by Atlas alone. But Atlas sets the boundary conditions for the update. There is also a quieter lesson about detection. We found Atlas quickly because it was bright and active far out. If there is a whole family of slower, darker interstellar bodies that do not outgas strongly, they will pass undetected. That means our current interstellar visitor list is biased toward whatever produces strong infrared or visible signals early. Atlas might feel unique because our telescope filters select for objects like it. That selection effect has not solved the anomalies. But it does warn us not to mistake a small sample for a full census. The retreat continues, and the last decisive data points are still ahead. The object will fade below most instruments' thresholds, leaving only long baseline astrometric tracking. That final tracking will tell us how far the non-gravitational acceleration truly persisted, and whether it matched the energy budget of CO2 venting or exceeded it. When that result settles, the story will narrow dramatically. Until then, the logical posture stays the same. The evidence supports two broad readings. Either Atlas is an extreme natural interstellar volatile object that forces a new class into our models, or it is a body whose coherence and material signatures are inconsistent with any currently worked natural pathway. The data on retreat has not yet forced the second reading, but it has also not given the first reading an easy path. It keeps tightening the same argument. Whatever Atlas is, it is not ordinary, and it cannot be explained by stretching ordinary comet physics a little bit. Soon the object will exit the solar system entirely. We will not get another chance to probe it at this level. What we learn in these last months is what will define how the next interstellar visitor is interpreted before the debate even starts. The final phase of Atlas's passage is the one science is least emotionally prepared for. Not because it is dramatic, but because it is quiet. When an object leaves, you are forced to accept either that you understood it or that you did not, and you don't get another close look to fix your mistakes. The retreat phase turns every earlier debate into a question of record. What remains measurable now is mostly geometry. The coma is thinning, spectral lines are fading, and the object is slipping beyond the reach of many instruments. But astrometry still works. Over long baselines, even small persistent pushes accumulate into trackable offsets. If the last months of tracking show that the non-gravitational acceleration fell exactly as CO2 production fell, then outgassing remains a complete physical explanation. The object stays anomalous in chemistry and structure, but the core dynamics remain natural. If the offset persists longer than the gas budget allows, then something else must be contributing. That something else does not have to be exotic. It could be a subtle radiation pressure effect, amplified by unusual surface reflectivity, or a high area to mass ratio. It could be a low visibility exhaust regime with very little dust. It could be a combination of small forces that normally cancel out in porous comets but remain coherent in a mechanically strong body. The key point is that something else would need to be stable, because the acceleration vector has stayed stable. This is where the coherence issue returns one last time. Coherence is the stubborn thread running through the whole story. Atlas has been coherent in chemistry, in outflow geometry, in acceleration direction, and in its resistance to surface disruption. Natural objects can be coherent, but natural comet-like objects are typically coherent only in one domain at a time. You might get a coherent chemical oddity in one comet. You might get coherent jet direction in another. You might get coherent acceleration in a third. Atlas kept coherence across all of them simultaneously, through the harshest part of the solar encounter. The outbound trajectory is the final check on whether that coherence was real or an illusion created by incomplete data. There is another quiet measurement that matters as the object fades: its residual brightness after activity dies. Once a comet shuts down, its brightness should follow a simple rotational and phase angle behavior. If Atlas becomes an inert point source, the light curve will tell us whether we were right about its size and shape. A large nucleus should remain visible longer, even without a coma. A small nucleus hidden by a bright coma should drop away fast. This is one of the cleanest ways to resolve the size debate without ever seeing the surface directly. A persistent inert brightness would support the larger body models and make the mechanical strength argument easier to accept. A fast fade would strengthen the idea that most early brightness was coma-dominated and that the true nucleus may be modest. Either outcome is valuable, but note what neither outcome does. Neither removes the chemical and dynamical anomalies. Size can sharpen the picture, not erase it. If Atlas turns out to be large, CO2 dominant, and structurally strong, then the natural reading becomes a new class problem. We would need to name a physical pathway that builds such bodies and ejects them in meaningful numbers. That pathway might involve CO2-rich outer zones around specific star types, or disk environments with lower water availability, or chemical processing that favors CO2 retention while water is lost. None of those options currently sits in our default formation narrative, but they are not forbidden. They would just be a revision written into the margins of planetary science. If Atlas turns out to be small, CO2 dominant, and still shows coherent acceleration and regulated activity, then the structural explanation has to do more work. A small body producing strong regulated thrust without shredding itself forces even tighter constraints on material strength and vent design. Small, fragile ice balls do not behave that way. A small, tough, vent-regulated, volatile body could exist naturally, but it is a narrower class than a large one. It would call for even more specific origins. Either way, the same consequence follows. Atlas would no longer be a comet from another star. It would be evidence that interstellar bodies include types we have not modelled. That matters because the interstellar population is not a curiosity. It is the background inventory of building blocks that every planetary system throws into space. Understanding that inventory tells us what is common in planet formation, what is fragile, and what can survive long enough to wander between stars. Atlas also forces a procedural lesson. Our first instinct when the third interstellar visitor arrived was to fit it into a familiar label quickly. That instinct is understandable because classification helps organize observation campaigns, but classification can also flatten anomalies too early. If your label is wrong, you measure the wrong things and you miss the right surprises. The Atlas episode is a reminder that the right sequence is data first, category later. It is better to say, "We don't know what this is yet," than to say, "It's basically normal," before the evidence settles. The exit phase also changes how we should think about future detections. If Atlas is a genuine natural class, then we should adjust search programs to look for CO2 first activity signatures at larger distances. We should refine models to allow mechanically strong volatile bodies, not just weak porous ones. We should update the expected distribution of inclinations and arrival geometries to test whether ecliptic near arrivals remain rare or become more common in a larger sample. If Atlas is not a natural class, then the operational implications are different, but still grounded in the same logic. We would need to treat unusual coherence as a diagnostic signal in future visitors, not as a curiosity to be smoothed away. That does not mean assuming artificiality whenever something is odd. It means refusing to force anomalies into comfort zones before they exhaust their predictive tests. In the end, Atlas will disappear into the dark with no fanfare. The solar system will go back to looking familiar. But the record will remain. The spectra, the light curves, the acceleration fits, and the geometry of arrival will be reanalyzed for years. Most likely, the story will settle into one of two stable conclusions. Either we discovered a new natural class of interstellar volatile bodies, CO2 dominated and mechanically coherent, or we discovered evidence that our current natural classes are not sufficient to describe everything that can pass through our neighborhood. The worst outcome would be to leave the story unresolved by treating its anomalies as separate trivia. The best outcome is to treat those anomalies as a single system of constraints and let the constraints define the category. That is what Atlas is, at minimum, a constraint setter. It is a rare object that forces us to say exactly what we think is possible, and to update that list if the data demands it.